All right, hello everyone. I would like to cover something that we didn't get a chance to cover as much as I would like in class, and that is how to deal with these uh, graph problems. So let's take a look at one example graph problem that was given in the homework. Before we tackle this problem, which asks you a whole bunch of different things, and I'm not going to give the exact solution here, but just tell you in general how to work with this problem. Let's scroll down for a moment and let me re-emphasize the relationship between velocity, position, and acceleration, but also emphasize something that we mentioned in passing, but maybe put it more explicitly here, how to interpret those relationships when we're dealing with graphs. So, as you know, velocity is the derivative of position, right? Because velocity is delta x over delta t, which when we take it to a limit of small time becomes dx dt, which is the derivative of position with respect to time. Similarly, acceleration is the time derivative of velocity. Acceleration is dv dt, or delta v over delta t. So going in this direction, we're taking derivatives. What that really means in terms of a graph, because you can take a derivative of a function, right? But it's hard to take a derivative of a graph. So what do we mean when we're talking about derivatives in terms of a graph? We're talking about taking the slope of the curve. So the slope of the position curve, if you're given a curve of a graph of position over time, then the slope of that of this imaginary curve that I'm showing here, that I'm pretending to show here, if the graph is increasing like this, then the slope of that increase at any given time, that slope is the velocity at that time, right? If it's sloping downwards, right, the position is getting smaller or more negative um, as you go, then that's the slope of that line, of that position line, would be negative, and you would have a negative velocity. Okay, same thing goes between velocity and acceleration. If you have a velocity versus time curve, then at any given time, the slope of that curve gives you the acceleration at that time. Okay, so now let's work it backwards. If we have an acceleration plot where we have acceleration versus time, and we want to figure out the velocity, in that case, what we'd have to do is we'd have to take the integral, right? If we do this in formulaic form, we would say that the velocity is the time integral of the acceleration, and similarly that the position is the time integral of the velocity. In terms of a graph, what that really means is that if you have something that's plotted acceleration versus time, then the area underneath the acceleration curve summed up is equal to the velocity. Right? So we'll look at that in a little more detail when we make an example. In other words, if you want to know the velocity at a given time from an acceleration versus time plot, then you would sum up the entire area underneath the curve up to that point, and that would give you the velocity at that time. When I say up to that point, I mean up to that point in time. Same thing for between the position and the velocity. To get the position from a velocity versus time graph, you would integrate up or sum up the area under the velocity curve up to that point of interest, that point in time of interest. Okay, so let's look at a specific example. This was a homework problem that has this curve, so I pulled it up, and we have velocity versus time in one dimension, Vx. So if we were to look at this, it starts off, notice here, of course, first that these blocks are steps of 2 in velocity. So this is 0, minus 2, minus 4, minus 6, minus 8, and this is minus 10, so this would be minus 12. Forward steps are in time. Time steps are in 1 second. So this is 1 second, 2 second, 3 second, 4 second, 5 second. Okay. If we were to be asked what the acceleration is from this velocity. First of all, to find velocity at any given time, you just read it off, right? Velocity at this time is minus 12, minus 12. Now it's up here. The velocity this would be minus 6. It'd be 0 here. at this time, at time 10, the velocity would be positive, it looks like 18, and so forth and so on. But what if we wanted to do something a little more sophisticated? What if we wanted to know what the acceleration is from this velocity curve? Well, again, the acceleration is the slope of the velocity curve. So here, the slope is 0 because it's horizontal. So that means that we have 0 slope, which is 0 acceleration. And that makes sense because acceleration means it's speeding up or slowing down. And here, over this time range, you see the velocity is constant at -12, right? Then it suddenly switches to having a positive slope. That means it's got a positive acceleration. It's accelerating in the positive direction, right? And as you can see, the velocity is getting less and less negative, and then it continues through 0 and becomes a positive acceleration. So then here, it flattens out again to 0. So now the velocity is constant at a positive number, but because it's constant, there's no speeding up or slowing down, so the acceleration is 0 again. And then here, because the slope is negative, this is a negative acceleration, which means it's being pushed back in the negative direction. So let's kind of get a sense of what's actually happening. So if I'm going to do this in kind of a discrete step thing, but we're going to try and pretend it's kind of continuous. So we start off at the origin, and at the first moment that we start investigating this, these kinematics, the velocity is at -12, and for a while there it stays at -12. So it's moving with a velocity that's negative, so it's going to move in the negative direction, indicated here by the red part of the bar. This is the origin. So it's kind of moving along in the negative direction. It's moving at kind of a constant velocity. Right? Then, at some point along here, when it gets to here, it stops moving at constant velocity and starts to slow down, right? Because velocity here is now getting less and less negative. It's still moving in the negative direction. It's still negative, but it's starting to slow down. It's getting not as large of a velocity. At some point, it slows down to the point where it has effectively stopped. And that would be here, where the velocity has reached 0. It then effectively turns around and starts moving with a positive velocity. Notice that it's still negative x, right? But it is got a positive velocity. If we wanted to know what the x was, we would start to have to integrate this area under the curve, right? It's now starting to move back negative. So when it got to 0 and stopped, it had moved this much, there's this much area under the curve up to that point. And that summed up would tell you what the x position is. Now we're moving forward. We're in this region where it's trying to speed up. The velocity is getting larger and larger in the positive direction. And so at some point it reaches a constant positive velocity. It reaches 18 meters per second, and then it stays at that velocity. Right, so then it reaches 18 meters per second, and it just stays at that velocity for a while. Right, so we're now kind of in this position where we're moving along at constant velocity. At some point, it crosses the origin again. What is that point? Well, the area under the curve, which we'll come back and look in more detail in a moment. When the area under the curve for the negative portion of the travel, for the times when it was moving in the negative direction, is equal to the area under the curve when it was moving in the positive direction, totally cancel each other out. Right? Then it has moved as far negative in the first half as it has moved positive in the second portion of the travel, and that would mean that it has gotten back to 0. So somewhere in here, when the area under this curve, this positive section, is exactly equal to the total area under this curve, that's when it crosses 0. Okay, so then it continues on, assuming, and it looks like just by eye, it will be somewhere around here where the area of this little trapezoid is equal to the area of this trapezoid. And it continues on with constant velocity. Oops, wrong thing. Constant velocity, and then it starts to slow down, right? So the velocity is still positive, but it is getting a negative acceleration. It's as if this thing was cruising along and then something starts pushing on it this way, pushing on the negative direction. There's an acceleration in the negative direction. At first, it's not enough to completely counteract the velocity, but it does start to slow it down. The velocity is getting lower and lower and lower and lower, but still positive. And then at the end of this experiment, we see that the velocity has slowed down to 0, and it just stops. And who knows what it does after this, right? If this curve went on to go negative, that would mean after it comes to a complete stop, it starts to go back the other way. On the other hand, it took an abrupt turn and go positive again, which means it came to a stop, paused, had its lunch, and then went forward again. All right, so let's go back to the origin here. All right, and let's take a closer look at the area underneath the curve, the integral. Right. If I were to ask you what is its position, notice that, let's look at units for a moment. This has units of meters per second velocity, and this is units of time. And you know, if I take the area of a graph, right, I would multiply, like if this were an XY plot, then the area would be X times Y, right? That would, like if you wanted the area of a room, right? If I plotted out your bedroom to get the area, and it's got this much width and this much height, then the area of the room would be just this times this, right? Same thing goes here, except now instead of multiplying X in meters and Y in meters, we're multiplying T in time with meters per second velocity. But when you multiply them together, the units are going to partially cancel. You get meters per second times seconds, and you're left with meters. And meters is the units of displacement, right? So when we add up the area underneath this curve, let's say we look at the first second. In the first second, let's say we're only interested in the first second, so I'm going to block out the rest of this graph partially. Right? If we're only interested in the first second, the total amount of distance traveled is just the area between this curve and 0. And that would be 1, 2, 3, 4, 5, 6 of these blocks. And remember, each block is 2 times 1. So that'd be a total of 12, right? Times 1 is 12 meters. So it would have moved 12 meters to the left. In the next second of time, right, if I say, what is it after 2 seconds? Well, then the area under the curve now extends to this size, right? And we now have 24 blocks, or 12 blocks in each block worth 2, 24 meters of displacement. So, and this makes sense. It was going at, remember, it was moving at a constant velocity. So after 1 second, it was 12. After 2 seconds, it's going to be twice that much. Continuing on, after 3 seconds, right? After 3 seconds, now there's this much exposed. So we would fill that in, right? And we're interested in only this portion because we're only interested at time equal to 3. Okay, great. So we now got 12, 24, 36 meters of displacement in the negative direction. That's great. And we would just keep going. Same thing for the 4th second, but then it starts to slow down, right? So now we have to learn how to deal with this strange area. If I asked you what the displacement was after 5 seconds, now it gets a little trickier, right? Well, first we keep this because this displacement has already happened, right? But we need to add this, and this gets a little tricky to do. Right? It's not really, it's kind of a weird trapezoidal shape, right? It's not a triangle, it's not anything. I mean, if we wanted to do the full, let's maybe start with something easier. If we wanted to do at time 6, we would just add this triangle that's under the curve to the area we already have. And the easiest way to do that is just to recognize that we could add another, let me create one here, another rectangle that is 2 more wide and down to 12. But what we would have to do is recognize that the triangle only fills half of this rectangle. Right? So we would take the area of this rectangle and divide by 2. And that's an easy way to do it. Right? And that would work. That will work for time 6. But at time 5, we don't have a full, complete triangle like that. What we have is some weird thing where it's really kind of a rectangle up to here. And then on top of that, we have a little triangle. So we would have to do that, right? We would add the area of this rectangle, which is straightforward, and then we'd add the area of this rectangle divided by 2, because that gives you that triangle. Okay, great. So let me say that we now continue on, and we want to study what happens at 6 seconds. So we would do exactly what I said, which is stretch this out. We now have this full triangle, but now it has come to a complete stop. Velocity is 0, and now it starts to turn around in the positive direction. Right, so if I asked, what is the displacement after 7 seconds? right? Well, we would just fill in this area under the curve, but we'll use green to indicate that it's moving positive, right? And in the next second, I would just add, oops, in that case, I have to then stretch this guy out here, right? Instead of that triangle, I would add this triangle, which again would just be this whole rectangle divided by 2, and so on, right? We would keep going, and you could just keep adding rectangles and half rectangles and triangles, etc. Right? So the next second, this much area is completed, and then it reaches a constant velocity and continues to cruise on, which means that the next second we would, let's see, I need this guy now. We would, oops, add this much, right, area under the curve. And then the next second we would add this much. And the next second we would add this much. And at some point, and I'm not sure exactly where because I haven't done the counting, when this area is equal to this area, this thing is now moving in the positive direction, right? This guy had gone here, slowed down, come to a stop, started going back the other way, speeding up, and then he reached a constant velocity, and now he's moving and cruising at a constant velocity. At some point during that region, I think, it'll cross 0 because the area under this curve will equal the area under this curve, and this negative and this positive will cancel, and the total net area under the curve is 0 because these positive and negatives cancel, and so the displacement is 0. And then we keep going, and we get this, and then we have to start adding these weird triangles and rectangles again, like that, and like that. And I think you kind of get the point at this point. All right, so that's the idea of how you would take a velocity plot to either use the slopes to get acceleration or fill in the areas under the curve to get displacements. Okay, and finally, there's a problem where they give you an acceleration curve and they actually ask you for displacement. And that's tricky, right? Because that's actually asking you to do an integral twice. You integrate a double integral, right? Which is hard to do in your head. So what I would recommend for this problem is that you actually draw yourself another graph, label it velocity versus time, and then do the first step. Do the integral just like we did with in the example above, except now they made it easy. They never have any triangles, right? So we're just going to be adding up the area under this curve, right? So at time 5, you can just say at time 5, my velocity will be, well, what would it be? It would be, we have 1, 2, the area under this curve would be 2 times 5, which would be plus 10, right? At time 10, it'll be 10 times 2, which would be plus 20, so it is going to gain 10 meters per second. I'm sorry, yeah, 10 meters per second after 1 second. We can start it with a velocity of 0. That will make life easy. So at 0, we assume it has velocity of 0. At 10, we will have, or at 5 seconds, we'll have 10. At 10 seconds, we'll have 20, right? And that's a constant acceleration, as noted by the fact that this is flat, it's constant. And then suddenly it jumps to 0 acceleration. Right? Well, if it's 0 acceleration, it's not speeding up or slowing down, so you can figure out what the next point should be. How much area do we add? Well, there's no area under this curve, right? So the answer is obvious. Then it has a negative acceleration, and we treat the same thing. This is negative, so the area under the curve will offset this a little bit, and you guys can figure out what the final velocity is. Once you have that velocity versus time plot, like you have the dot here at 0, and then it went up to a certain thing, and then it went up, and then it stayed stable, and so forth, then you can treat the second half of the problem is if I want displacement and I have a velocity versus time curve, well, that's exactly what we had here. So you again do the integral and you figure out at each time point how much space is under the velocity versus time curve, and you will get the position. Okay, so hopefully that will help you guys out in trying to figure out how to do any of these graph type problems for 1D kinematics. And as a note, I've extended the homework deadline to Monday so that you guys can go back, and those of you who had a hard time with this, now that I've actually spent some time explaining it, I want you to go back and see if you can get the right answer. Okay, have a good weekend, guys.